CBAF, the Continuous Electron Beam Accelerator Facility, is a new laboratory for basic nuclear physics research. At CBAF, scientists can advance our understanding of matter itself by probing the quarks and gluons in the atom's nucleus with beams of electrons from a superconducting accelerator. CBAF has an educational mission as well. The CBAF Science Series features scientists and engineers who are gifted at making their work not only informative, but fun. The Science Series is held once a month during the school year in the CBAF Center Auditorium. The presentation is live, spontaneous, and for the most part, unrehearsed.
Good evening. Good evening. This only works for the camera. Good evening. Welcome to the first program of the 1994 Winter-Spring Science Series. I'm Beverly Hartline, an Associate Director at CBAF, and it's my pleasure to introduce tonight's speaker, Dr. Thomas Cahill from the University of California, Davis. Dr. Cahill grew up in rural New England, where his whole elementary school had 16 students. He was always interested in animals because he lived in the country and in science, and he wanted to be a veterinarian until a very effective high school physics teacher convinced him that physics was really where things were at. His wife, Virginia, is an environmental lawyer, and he has 2 children, one of whom, his daughter Catherine, is in graduate school at the University of Washington in atmospheric sciences, and his son Thomas is a senior at UC Davis in wildlife biology. So I guess science runs in his family. He went to Holy Cross College in Massachusetts, got a degree in math and physics, got a master's degree in physics, and a PhD in nuclear physics at UCLA. He's held many positions in his distinguished career and has gotten, in the last 20 years or so, extremely active using a small accelerator called the cyclotron at the University of California, Davis, which was actually moved there secondhand from Ernest O. Lawrence's own laboratory at the University of California, Berkeley, where he's been involved in doing all sorts of research in environmental science, in nuclear physics, and even in medical treatment. He's going to tell us a lot about some of the recent environmental science detective work they've used this accelerator for. And please join me in welcoming Dr. Cahill.
Well, actually, I'd like to welcome you because we couldn't get this many people out in Davis if we gave free pizza, so I'm impressed. I'm really pleased to be here, and I only have one little worry, and that is typically when they bring some guest speaker in, the impression given by the students is sometimes the wrong one. And the 2 impressions that are often given is, one, that, gee, that was a neat problem, but he already solved it. Nothing left for me to do. And the other one is, God, it's a tough problem. I'll never be smart enough to do that kind of work. And so my 2 points tonight are that there are great big problems out there that need people to work on it. And secondly, that you people can do the work. Every one of you. And I'm going to show that by 2 ways. Now, first of all, I'm a professor. So I'm going to assign tonight homework. I'm going to actually give you a homework assignment, take-home assignment. It's due in 2 weeks to Beverly. She will send them all to me at Davis. I will grade them personally and mail them back to you in a stamped envelope. And I trust your science teachers, your math teachers, will be generous beyond all measure when they get this paper in terms of your program. Now, the reason I'm doing it is because I'm going to point out some people who really have screwed up big time in science. And you've seen them on television, they've made statements and so on, and a well-trained science student at the high school or college level can easily do the research to check these things out yourself. Don't depend on somebody else telling you what's going on. You can do it yourselves. And I'm going to use the example of the debacle over the Kuwaiti oil fires as my prime example. But first, a little background. As Bev said, I was also to be a vet. I would have been rich by now if I had been it, probably. But I had a good high school science teacher, and he got me interested in physics. And I switched from math into physics 4 months, before Sputnik was sent into space. Now talk about timing, okay? So by the time I graduated, there were fellowships lying around on the street corners. And so I got into UCLA with no problem and found out for the first time in my life I had to really work. But I really liked what I was doing, and the people who were working there were building the first relativistic cyclotron, a small accelerator, that was able to get into the relativistic proton region using a new technique called sector-focused cyclotron. And they really enjoyed themselves, and they played hearts every noon, and they had a lot of fun. And I said, hey, this looks more like fun than work. So I got involved in nuclear physics, and it was a great time in the 60s. I went to France with my French-speaking wife, had a wonderful time working at Seclay, and then had to get back to the United States and do serious work. I went to Davis because it had a cyclotron. The cyclotron was an old machine. In fact, it was the old 60-inch machine from Berkeley. The cyclotron and I are within 4 months of the same age, 1937. And it's still running. It's the oldest living dinosaur. It's a cyclotron that was used to discover neptunium, plutonium, and because Berkeley is so modest, berkelium, californium, and so on. And it was brought to Davis, and I'm going to give a little history of the cyclotron and explain how I got from nuclear physics into air pollution and Kuwait and whatever. So if you can kill the slides now, I'd like to have the first, kill the lights. This is a picture of Ernesto Lawrence in the center, Robert Oppenheimer. There's about 6 Nobel laureates in the picture. This is in 1937. Now, Lawrence had built one small cyclotron using an old magnet that was found in a warehouse. He wanted to build a big one, but there was no money around. Grants were really the pits in 1937. But he convinced Regent William Crocker that the cyclotron could not only do basic research in physics, but, and he used his own words, test a new way to treat the age-old scourge of mankind, cancer. Now that sounds very modern somehow, actually. If this laser still works, it'll be a miracle. Okay. And so that the machine was built not just to do basic nuclear physics, but to do a mixture of basic and applied physics. It's the old 60-inch cyclotron. So the theory was, from the very beginning, these machines had multiple uses. This is Lawrence. He always wore coat and tie. He never actually did this work at all himself, but he was posing for a picture. This is 1939. Now, Lawrence had an idea that by taking the same particle around again and again, you keep adding energy every time it goes around. And of course, that's the principle, in many ways, behind CBAF. So here's a cyclotron as seen by the inventor. The particle starts at the center, like hydrogen, goes around. Every time it goes around, it collects 100,000 volts. 10 times 100,000 is 1 million. 10 times a million, 10 million. And at the far end, you pull it out, and you set it on its way. Simple concept. The cyclotron is seen by the inventor. Cyclotron is seen by the visitor. This is pretty accurate, to be honest with you. It gets very complicated very fast, you know. But it does work. It can be built. It's a fairly small machine. Ours only weighs about 300 tons. Now, that is Berkeley. There's the San Andreas Fault. And here's Davis, right about there. Davis in the Sacramento Valley. Now, Davis was the agricultural campus of Berkeley for many, many, many years. Berkeley claims it still is. Okay? But in fact, in 1947, it became an independent campus. It has about 25,000 students. But it is rich in heritage, shall we say. There is some of the heritage that is approximately 100 meters from our beam dump. Now, Fermi Laboratory has buffalo. Davis has pigs. Okay? And we do regret it. So the Davis campus was a wonderful place to do research because, why? Because we could join the physical and biological sciences and treat new ways to treat the age-old scourge of mankind, cancer. Did we do either? Not. Because the AEC only funded basic science. Now, many of us realized that we thought possibilities in applied science. And we asked Glenn Seaborg personally for permission to have the Davis machine do some work in applied science. And his answer was, no. You're doing great physics. You're in no danger. Go to it. So we did what anybody does. We cheated. We cooked the books. We came in the weekend and tried new ways of using the machine for applied research. Now, this is the cyclotron laboratory. Seen with the laboratory director. The picture's out of focus, but that's Napoleon. And these people over here are who? Students. Davis is rich in students. Now, the view is a little different from Washington. This is the cyclotron as seen from Washington. I like the fact that the kite and the wind suck are opposite directions, too. No, the money going in and the trucks coming out. So, this is a tough time for science. They were building machines. There were many university facilities that were being shut down right and left. But we were in no danger, right? Not. This is the period when we were supported by the Atomic Energy Commission. And then this is 1972. And suddenly, miracle of miracles, we ran out of money. Now, the normal thing to do is to shut the thing down, but many of us had gotten started on using the machine for what Lawrence wanted it used for, to join the physical and biological sciences, ... And we had several advantages. And this is one of them. A student. Slides backward, too. We have lots of undergraduate students, and the machine is right on the Davis campus. So the students are the heart of the survival of our cyclotron. High school students, undergraduates, and graduates. Interesting also, Dr. Carlos Castaneda, his brother-in-law was killed by a death squad in El Salvador. And I was able to get him to get a visa for the United States. And he's a very, very fine physicist. So there's several advantages. Now, of course, the students see the cyclotron roughly the same way that Ernest Lawrence did. It's a simple machine, a tool to do what you want to do. But what do we want to do? Well, here's a second advantage. If you stepped off the airplane in Los Angeles tomorrow and breathed deeply, that's what you would get. Highly hydrated ammonium sulfate, LA smog. California has a touch of smog. I got a touch of cold. And in fact, the university was desperate to have various techniques used to study air pollution in California. And we thought that the physical techniques of the machine, I've got it right here. I came across the country with a cold, would be useful for studying air pollution. Because why? Existing things weren't working. Why weren't they working? Because the smog was so complicated that the chemical techniques available for such a small amount of mass were not able to answer the question, where did it come from? What did it do? How dangerous was it? And especially, how does it scatter light? I'm a physicist, I'm not a doctor, and so I'm more interested in this kind of problem. The machine now became a general purchase machine, and this is a cyclotron here. It's about 2 meters across. This beam line does nuclear chemistry, air pollution, and the Gutenberg Bible, basic physics, and Dead Sea Scrolls. The missions to Jupiter and Saturn, Galileo, the deeply mourned Mars Observer. All these were, in fact, tested out here. A lot of work for the Navy is being done on here in satellite work. Thermonuclear fusion, basic nuclear physics using neutrons, radioisotope production, so on. And between all these sources of money, the laboratory was able to be glued together. But it was very difficult. We lost 2/3 of our staff. But by 1978 or so, we have enough money coming in from the applications of physics to the environment. The laboratory became effectively self-supporting. And so we had this terrible strain. For 20 years, only 5% of our money came from the university. The other 95% was, in fact, raised outside every year. The good news was everybody knew they were in the same bucket. So we had to be good. We had to also be cheap, by the way, too. Now, I don't recommend that for anybody. It's a terrible way to do science. But it's certainly better than closing down. And it led to a rather innovative program that we're kind of proud of by now. And the laboratory now, by the way, has grown to the point where it's almost $5 million a year. And there's nobody that can shut us down because there's nobody that pays us. Now, this is one of the examples. This is one of the beam lines. This is about 5 feet high. This is a place, this is a Bell & Howell slide changer. Cost $12.50. Modified the cost of $5,000 to work under the computer and in vacuum. Now, what we did was we took the samples you saw before of air pollution, and we captured them on filters. Now, we don't analyze gases. We analyze particles. We bring them to the cyclotron, we put them in the beam, and the cyclotron beam then gives us our second great advantage. When the beam of protons passes through the material at 4.5 MeV, every atomic state is simply excited without any selection. Because our third great advantage was we knew we were stupid. I'm a nuclear physicist. I don't know air pollution. I don't know the Dead Sea Scrolls. So what I did was, rather than try to guess, I measured everything. Physicists can do that. Hydrogen to uranium all the time, for $32 even. Now, the nice point about this is, here's a sample, and every element has a characteristic bump at the right location. Now, this is chemistry as done for a physicist. They're all in order. Aluminum, silicon, phosphorus. I mean, I always get confused by valences. You know, my chemistry wasn't that hot. But I can count, right? Copper, zinc, lead, and so on. And that's the way we're going to do it. If there's a whole bunch of chromium, there's a big peak right there. If there's no chromium, there's nothing. I don't have to guess. Experts guess, we don't guess. And that's where we're still funded. Now, the area we got into, which led us into Kuwait and to some problems, is the question of visibility. I showed you a tape earlier before the meeting. I'll show it afterwards too. This is from the National Air Pollution Assessment Program on haze. What the haze is, where it's going, and so on, because it appears to be tied to many forms of air pollution. Now, as the tape showed, the visibilities over here are rather poor, generally less than 10 miles in the summer. Out here, more than 70 miles. Now, our job was to measure all around the country, find what was there, and if it's causing a problem, shut it down. Now, these are some slides. This is in the Yosemite National Park, 1/4 of all days are this good or better. But 1/4 of all days are this bad or worse. Great Smokies, 1/4 of all days are this good or better. This is the summer median. That's the average day. And 1/4 of all days are this bad or worse. That is not natural. So these are our sites as we had a couple of years ago. We now have another 20 sites in here. And the sites are generated by samplers built at Davis. They're staffed by our people who set them up, and then they're run by the people of the National Parks and Monuments. And all the protocols from the beginning to the end have been designed around what? Around the cyclotron. We do everything differently. You can't do one piece of it. The whole program has to be integrated from top to bottom. And we luckily had the freedom to do that. This is an example of sulfur across the U.S. Note the sulfur levels are very high here, but the visibility is low, and very low out here. This sulfur comes from smelters, coal-fired power plants mostly. So, these are examples then of the attribution techniques. Now, there's one problem with this program. Look at that slice right there. What's that called? Other. Can't do that, right? Other. What was it? It turns out the other was mostly organic material. But how do we measure organic materials? We only have 1 microgram of sample. We use the oldest, best-known technique in all of physics, proton-proton scattering. Nothing could be simpler. But organic matter has hydrogen. We measure the hydrogen, and lo and behold, using a cyclotron, we can get hydrogen very easily, very well. And that program alone allowed us to take that thing and label about that much of it as organic matter. Just for kicks, by the way, here are the sulfur dioxide sources in the U.S., and each circle is proportional to the size of the source. I'm happy to say that that source is now controlled, that source is controlled, that source is shut down, 2 of these are controlled, and the third is shut down. Now, because we were involved in this work, because we had this, we were very anxiously interested in what happened when the first news came of the oil fires in Kuwait. As you know, about 600 oil wells were torched off. And during this early period, this, by the way, right there is Kuwait City. This is smoke. The coastline goes like that. And it's all smoke from fires. 6 million barrels of oil were being burned every day. And there was much comment from very well-placed people about this was going to be a disaster of global proportions. Now, for your homework assignment, if you choose to do it. I'm going to have you take and evaluate that hypothesis. It was widely used on Ted Koppel. It was widely seen in the newspapers. It was presented by people who are members of the National Academy. But you people have the capability and the ability to check that out. What I'm going to ask you to do is I want you to compare the oil fires in Kuwait to the forest fires in Yellowstone for CO2 production, and compare the oil fires in Kuwait to the U.S. sulfur emissions for SO2. On the tables outside, you'll see the sheets of paper. They're due in 2 weeks, sent to Beverly, and be mailed to me to Davis. But I want to prove to you that with the knowledge you have right now, anybody in high school, and a lot of people below high school, can take it and do your own analysis and understand that what these people said was verged on excrement. Okay, so killer smog. Oh, we've heard killer smog. It's going to be killer smog. Note the teeth. Well, it wasn't killer smog. The point was that we don't have to guess. Nuclear and atomic techniques are so potent that we can do all kinds of things. But how do you get there? Well, first of all, that is our air sampler. The size of the fist. That sampler plus a pump is perfectly capable of giving a sample that mimics your own lung. We developed it at Davis. It cost $28. Replace the unit that cost $5,000. Because the universities are traditionally poor, we had to do things differently. And this unit could fly in an airplane. The big unit could not. So the next thing is you have to want. This is a Landsat photograph before, after. These are the fires right here. You see little red dots. For various reasons associated with a problem called, among other things, nuclear winter, the Defense Nuclear Agency made $1 million available to the National Science Foundation to do special studies over Kuwait. Now, it's interesting. This work is the work that we did in our own program at Davis. We were paid for none of it. And every one of those programs was honchoed by a student because they're interested in what was going on. And our great advantage is students are very curious people. They want to find out, they want to work. So we did not need, all we needed was the opportunity to fly our samples. So we flew on National Center atmospheric side, 10 samples. We managed to find examples of oil well. Turns out that was a governmental secret of Kuwait. We managed to find a friend of mine at Caltech who knew a friend of his at another company who happened to have 8 samples, which we gently borrowed for the moment. But the point is we needed the information. We saw smoke from the fires go by Mauna Loa Observatory in Hawaii. We have a station. And finally, with the help of the Minister of the Environment of Kuwait, we placed impactors actually in the burning fields. In fact, they were driven to the field in a Mercedes-Benz. The guy put in the back of his seat and drove out of this mucky field, and the stuff was raining over his car. And he told the U.S. Corps of Engineers, get me power. And in about 3 days, they had 110-volt power. And that's the only samples taken in the actual fields. So the next thing is, you want to do it. Now, these are examples of what we saw. This is about 10 micrometers around. Remember the video I showed you earlier? The typical size particle that scatters light is about the size of that little dot right there. These things are enormous. They're great big fluff balls. They're soot and carbon and so on. And they're so enormous that they travel long distances. But look at this stuff here. What's that rock-like stuff? Turns out it's rock. When we analyzed the samples, we found out something we should have known earlier. Namely, that Kuwait was the dirtiest city in the world, according to the United Nations, before the fires were turned on. Why? It's full of dust. And it turns out that 70% of some of our samples was fine dust. Further, the amount of mass measured, that's 70 micrograms. The U.S. federal standard is 150. That means that in the actual fires above Kuwait, in the plain, the dust that was measured was 1/2 of the U.S. EPA's own standard. That number is less than it also. So the point was these numbers weren't so scary. In fact, it turned out that the average sulfur over Kuwait in the cloud almost exactly matched that at Shenandoah National Park in the summer or Los Angeles anytime. Further, the toxic metals. Toxic metals. Hey, we couldn't see them. There weren't enough toxic metals to see. So what do we use? We used Star Wars. We used a free electron laser from the Stanford Linear Laboratory designed for Star Wars and modified it to analyze smog. Now, that was through Livermore. But it's the same kind of thing that we can do here at CBAF. Very much the same operation. The point was, you've got to want. And we put the thing in front of a laser at Stanford, and we measured the vanadium nickel, and lo and behold, it was less than the average values in Long Beach, California. That's billionths of a gram, 9 billionths of a gram. The point was, you don't have to guess. These white plumes, they were so mysterious. What were they? Natural gas and salt water. Once the well ran out of oil, the natural gas comes out, brings the salt water. Those are salt plumes. Yeah. Now, that's it for the slides. So what happened? So what happened, we found out, was that Kuwait was not, in fact, nearly as scary as people thought. What had happened was that as the Kuwaiti fires burned up, the soot, the sulfates, the acids mixed with what was already there, namely dirt. Sulfur is acidic, dirt is basic. You mix acid and base together, what do? They neutralize. So the cloud did not rise to the stratosphere like it had been predicted. It in fact stayed quite close to the ground. It dissipated quite readily, and the environmental impacts were bad locally, minor regionally, and zero globally. Now, if the story had stopped there, we'd have simply a nice set of papers and people would make tenure, right? But in fact, it started something very interesting. It started a reevaluation of some problems that have been bugging us for a long time. And it's the problem of global climate. Now, here's an area where there's a lot of garbage hits your newspapers. Arctic shows no sign of greenhouse warmth. Is the greenhouse effect dead? Should we forget about it? What about the Rio meeting? What should have been our science? This is a standard embarrassment, and it turns out the Kuwaiti fires helped us solve it, because it showed, therefore, that we could look at the Kuwaiti stuff and know what's going on. So now, I'm going to give a little bit of the science on global climate. Is it worthwhile spending your career studying global climate? Not a bad idea, right? There's a problem that needs a lot of good thought, a lot of good time. Now, this is an example of a wave, a light wave, hitting a particle and bouncing off it. Now, it turns out that, right here, that visible light interacts with aerosols. Aerosols are any solid or liquid particle floating in the atmosphere. Infrared light interacts with gases. CO2, H2O, all those things. Visibility is both urban and remote, and global climate is heating, but it's also cooling. Are we actually cooling the world up? Now remember, if we did not have a very good balance between the energy coming in from the sun and energy going out from the sun, we'd either fry or freeze very, very quickly. The Earth is in very gentle balance. And what's the nature of the balance? The balance is a balance between the energy coming in, which is in the optical band. Here's a spectrum from the sun in space, right like that. What gets to the ground is this. In Los Angeles, looks like that. This is about 1/2 of that. Here's the blue, here's the red, ultraviolet. All you people who are professional tanners, be aware. And over here someplace is infrared. Now the Earth, does the Earth in fact give energy back? Yes, but in a very interesting and complicated way. And this is a rather messy graph, so I hope you'll pardon me for this sucker because it is not easy. This is the Earth, clunk, 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 clunk. This is space, you know, the final frontier. Okay. Here's the sun over here someplace. 100% of the light comes in. Now as the light comes in, it hits the atmosphere, and 31% bounces back to space. What's that called? Clouds. It's what you see. 3% goes all the way down, hits the surface, and goes back to space. So 31 plus 3 is 34%. So of the sunlight that comes in, 34%, it's bounced back into space immediately. 19% heats the atmosphere. 50% goes down here, and 47% goes in the ground. So this is what happens optically. But over here we have our famous greenhouse effect. I'm sorry, this says greenhouse. Infrared is a much longer wavelength light. It's 10 microns long. Visible light, half a micron. And the ground puts heat back to the atmosphere and warms it up. 119%. 6% goes into space. But the atmosphere goes back and warms the ground. And only a small amount goes out to space. If you take 60 plus 6 is 66, plus 31, plus 3, 100%. 100% in, 100% out. But what happens if somebody screws up and adds a little more or a little less? The Earth can always arrange itself by getting a little bit warmer or a little bit cooler. Now, this is tricky, by the way. You know what that is? El Nino. It's the heating of the tropical oceans, giving us worse and stronger hurricanes, which are not unknown on the Virginia coast. Watch it. So, with that in mind, we can now go ahead and put Kuwait in proper perspective. Here is a solar model of the net energy. 0 means you're in perfect balance. 1.5 watts per meter squared. 3 means we're warming up. -1 means we're cooling off. Here is the heating of the Earth from the greenhouse effect to the CO2. Add methane and everything, it goes up to here. Where's Kuwait? Right there. Negligible effect. But during the course of the Kuwaiti world, some scientists realized there was something wrong here. Namely, that they had screwed up some aerosol calculations 15 years ago. So they redid them. And what did they use? They used this. Remember these visibilities that were so bad? Have you ever flown across Shenandoah in an airplane in the summer on a clear day? Look towards the ground. Is it green? No. It's gray. It's gray by a mist that hangs over the ground, but it's not fog. What is it? It's sunlight being reflected back to your eye. It's scattering by aerosols. And scattering by aerosols takes this little number right over here and makes it bigger. Scattering by aerosols puts light right back into space. Now, since you're all mathematically competent, let me tell you, the sunlight coming in is 1,400 watts per meter squared, roughly. Now, if 0.1% more was pushed back into space, how many watts per meter squared is that? 0.1% of 1,400 watts per meter squared. Count of 1, 2, 3. Trust yourself. You know it's 1.4, right? You would have found it anyway. Okay, 1.4. So if this goes from 31 to 31.1, that cooling counteracts all of the CO2 heating. But aren't there global models? Haven't we seen them in the papers? Aren't they in Rio? And I say to you, garbage in, garbage out. Modelers are not measurers. Experimental scientists are the killers of science. We live for destroying models. We thrive in ripping apart theorists because there are not enough measurements made in the world and there's far too much speculation. And speculation gets you in real trouble. So, what happens? All of a sudden, all the stuff we've been doing with the National Park Service starts to look very good because we have those measurements. A paper by Charlson and so on shows all of a sudden what happens. There's Kuwait, here are the clouds, and here's the sulfate aerosol, the same sulfate aerosol that makes Shenandoah and Newport News and Great Smokies look so miserable in the middle of summer. That sulfate aerosol is cooling the world. What's going on here? Well, no sooner had this happened than what happens, Mount Pinatubo comes on an experiment I could never have afforded doing. You know, put a grant at the NSF, buy me a volcano and blow the heck out of it, okay? Pinatubo kicks up so much sulfur in the atmosphere, it makes the sunsets gorgeous for several years. Why was it gorgeous? Because the sunlight was being bounced off it. What was the color you saw? Almost pure sulfuric acid. Now, when you have a date out sometime and you watch the sunset and it looks all orange, you say, you know, darling, that's almost pure sulfuric acid. I think that is not the right approach, okay? And luckily, we had measurements. And the measurements showed that for North America, we'd cooled North America by 0.8 degrees Celsius, almost in perfect agreement with what the aerosol should do. That's an experiment. But you would not see it if you had not looked. There's none so blind as those that will not look. So we've got some jobs to do. Now, coming into this thing, in that same article, they plotted where, in fact, the sulfates were. And where are they? An enormous blob over Eastern Europe. You all know about Eastern Europe. Disaster, okay? China, Japan, not good. Newport News, not great. Now, in red, I put next to it the actual values of measured aerosols. The model predicts 10, here it's 8. Not bad. Model predicts 6, here it's 1. Now, if you were off by 600% in your math paper, not even Doonesbury would give you a B+. Supposed to be 4 was 1.3. Supposed to be 2, 0.5. Supposed to be 4, 0.6. Now, this is not a good match between theory and experiment. What's needed? What's needed is a vastly improved number of measurements of actual aerosols quantitatively, as a function of size, as a function of chemistry. And who's going to do it? There's 125 laboratories around the world with small accelerators. The physics justification for them has pretty much been shot. But any one of them could take these techniques, take these simple instruments, put them together, and do world-class research in global climate. That's what's needed. What we have to do is turn from a destructive program where we shut the machines down and put them so they become useful. The nuclear and atomic techniques take us a long way towards answering this problem. Because why? The machines are there, the people are there. Are the machines great? No. Are the people great? Yes. They're the best and brightest. And where are these machines located? All the places you want to make the measurements. We have one in Bangladesh. You know, hard to think of Bangladesh having its own accelerator, but it does. You know, all around the world. So the point is, by getting the people involved with this, we're now setting up something called Global Atmospheric Watch. And the half-baked, inexpensive techniques generated by UC Davis have now been accepted by the United Nations. So we're stations being put out. But our job is not to measure the stuff, not to bring it back to Davis. We provide quality assurance, we help them out. We want the people who are there to do the work themselves. Now, by doing this then, we allowed the people doing the work to be present and understand what's going on. And that's why I think we have to get people, all kinds of people, involved in science again. Now, finally, do another example. You've all seen this graph, I hope. This is a graph of carbon dioxide versus time, showing it rising very sharply, 1850 to 1990. Watch this approach zero. And below is a graph of methane in the same period. And these are the major greenhouse gases. Now, based upon these, we should have seen, in fact, an increase in temperature roughly on the dashed line. What did we see in North America? Flat. What's going on? This graph was being used to support this graph at the Rio conference. And it really bugged the heck out of me, because it was not a good representation of the data. But now, look what happened. World War II, massive increase in sulfur aerosols. Tennessee Valley Authority went from hydropower to coal. But worse than that, they actually cleaned their plants up to some degree and took out the fly ash, which is basic, and left the sulfur, which is acidic. We have generated machines for making vast amounts of acid and placed them all across the eastern U.S. Now, if you put the sulfates in, the sulfate predicts that in the northern hemisphere, the temperature should be constant. Now, this graph becomes, in fact, an affirmation of global climate. Global climate done right works. But there's good news and bad news. If we clean the sulfates up, we're going to get warmer. So, anyway, anybody who's heading on out, grab some of the homework problems you like and work them out. So, the conclusion of the program is the following. We think we know what's going on now, but we're probably wrong. Oh, let me one more graph here. Do we know about carbon? Yes. What if I said today, okay, I got all the power in the world, I'm going to ask the entire world to keep the same level of CO2 for 8 years. How hard would that be to do? Darn hard. But we did it between 1978 and 1986 because of the price of oil. Total world production of carbon, burning it, was constant. Did the CO2 slow down? Not one bit. Bad news. So, I think that the Kuwaiti experience has taught us some things. The Kuwaiti fires were analyzed by cyclotrons and by synchrotron radiation for the first time and quickly gave information on this. It was not as bad as we thought. And in fact, if you do the calculations, you'll find out that the Yellowstone fire and U.S. sulfur are roughly comparable in some ways to the Kuwaiti fires. It killed the theory of nuclear winter. People wanted to believe the theory because it made nuclear warfare less likely, but it was a bad science. It reopened global climate to aerosols. The National Park Service visibility data suddenly becomes the key to understanding global climate. We have 10 years of data on this. And Mount Pinatubo fortuitously blows its stack. Solved, quote unquote, ask me again next year if we solved it, a major problem of greenhouse effect, and we now need global aerosol data urgently. The component everybody ignored now has become the most important component. Well, I think in a summary, I want to just give you an idea that what comes first is the work. You've got to want to do something. There's plenty of good problems out there, and there are lots of tools. What I view is the following. Every nuclear physicist who's ever lived and worked for me. They developed new theories and techniques and ideas which I can use for my research. All of a sudden, there are so many problems, we need a lot of bright people out there. I appreciate you coming out and you coming out this evening. It's cold out there, a little rainy, but stick with it. We really need you very, very badly. And thank you for coming.